We're going to examine Backus-Naur form. Now, Backus-Naur form is a context-free language. Now, to understand context-free language and why we need them, we just need to first look at regular languages where we might have strings within a regular language that can be represented using regular expressions or finite state machines. But there are some languages that are too complex and can't be expressed using regular expressions. So in this situation, we'd use a context-free language as an alternative. And a context-free language is necessary for languages like programming languages. Natural languages are way too complex to be represented by context-free language. So natural language is what I mean by that is a spoken language like English. But all regular languages can be represented using context-free languages, but that's not to say that all context-free languages can be represented in a regular fashion in the way that we've already described. So Backus-Naur form is an example of a context-free language that we're going to explore in a bit more detail now. Backus-Naur form is expressed using a set of what we call production rules, and they take the following form, where we have a left-hand side that is defined by the right-hand side. On the right-hand side, we often have terminal symbols, although we can have non-terminal symbols as well. And on the left-hand side, we have non-terminal symbols. These are indicated by chevrons on either side of the symbol itself. We can also have a choice between different symbols as well, as indicated here by the pipe, the vertical line. Let's have a look at an example of a Backus-Naur form production rule. We can say that a bit is defined using the following production rule, where bit is our non-terminal symbol here, and our terminal symbols 0 or 1, and we know they're terminal symbols because they don't have any chevrons either side of them. And we can have it such that a bit is defined by either 0 or 1. We're going to look at a second example where we have 3 Backus-Naur form production rules. Before we get to this though, we need to understand that if there's a non-terminal symbol on the right-hand side, there should be another production rule with a non-terminal symbol on the left. So let's have a look at the example we have here, where we have on the right-hand side, we have non-terminal symbols of month and year. Therefore, we need to have a non-terminal symbol on the left in this case. So year is defined here as any 3 years between 2018 and 2020, and month is any month defined by the number of the month during the year, so between 1 and 12. So that's our set of production rules, and that will allow us to have valid expressions here for any month of the year between 2018 and 2020. There is a shorthand we can use to represent our terminal symbols in this context. So instead of writing out all our months individually and all the years separately, what we can do is we can indicate the range that we have here. So we have a range of years from 2018 to 2020. We can put those in square brackets, and we have a range of months from 1 to 12, put those in square brackets. But anywhere else we have ranges, for example, range of letters, we can apply the same idea. Recursion in Backus-Naur form allows us to have one or more of a given symbol. Let's just have a look at an example here where we have an integer that can either have a single digit, it can have 2 digits, or it can have 3 digits. And the problem is with this is that the maximum value that we could get for an integer using this setup here, this production rule for integer here, the maximum value we could get is 999. And of course, integers can have any number, any arbitrary number of digits. So we need to represent recursive production rules that allow us to have integers with any number of digits. Now in Backus-Naur form, the rule below here states that we can have an integer with any number of digits now. So it's recursive because integer is defined in terms of itself and appears on both the left and right hand sides. So in a similar way that a recursive function calls itself, we have here integer defined in terms of itself. We also in this case have a base case and a general case. The general case is a recursive part, and the base case in this case is simply digit on its own. So let's have a look at how we define 321 using a recursive production rule. So this is our production rule again. Our integer on here is set to 1, it's just a single digit. Then what we do is we take our next digit, which is 2, and essentially append it to integer there. And then we take our third digit, 3, and again append it to integer, which gives us now 321. Now, if a production rule has recursion, there does need to be a non-recursive case. The top example here is invalid because it doesn't have a non-recursive case, doesn't have a base case. And then the bottom one here is our perfectly valid production rule that has both a base case and a general case.